Hi, and welcome to the Opex August Analytics Academy session. Today, as you can see, we're very happy to welcome Gurobi CEO Ed Rothberg for a fireside chat on optimization with our own Mike Watson. So for those of you who may not know, Ed has his PhD in computer science from Stanford University. He is also one of the world's leading experts in computational optimization and is particularly well known for his expertise in the areas of sparse linear algebra and mixed integer programming heuristics. Ed led the CPLEX Optimization Team for 10 years prior to moving on to co-found Gurobi, which is today's most powerful mathematical optimization solver on the market. So let me quickly run through a few regular housekeeping notes, and then we'll get right to it. So as you have noticed, you are all, as attendees, in listen-only mode. This is really to ensure minimal disruptions in the presentation, but you do all have a direct line to me using the question section of the GoToWebinar panel. Mike and Ed are going to take some time at the end for Q&A, but feel free to submit those questions as you think of them throughout the webinar, and I will queue them up to ask at the end of the presentation. As a side note, if we don't get to all questions out loud today, we will either get you a direct response through GoToWebinar or follow up with an email after the session. So with that, I think we can go ahead and get to it. Mike, I'm going to turn it over to you.
All right, thanks, Sarah. So Ed, I'll just start right off. As an expert in optimization, how do you like to explain optimization to business users, savvy business users, but still business users?
Thanks. Well, actually, before I dive in, thanks for the introduction and thanks for the invitation. Looking forward to our conversation. So, yeah, I mean, when it comes to optimization, the sort of the blessing and the curse of optimization is that it's so versatile, so broadly used. And so, when it comes to talking to business people, ultimately, the first thing I say is, if you've got complexity in your organization, some set of constraints that is hard to meet, you've just noticed in your operations that there are things that you could be doing better, that there's probably an opportunity to apply optimization to the business.
Cool. And where do they get hung up on that? Like if they misunderstand you in some way, is there areas
Sure.
where they don't quite get it, or?
Yeah, I mean, it's so in my experience, it seems that it's human nature to try and put everything in a category, in a box, if you will.
Yeah.
And so, when I talk to people about what optimization is and what it could do for them, it's just clear from the beginning that they're trying to figure out what box to put you in. So, talk about, we help to schedule manufacturing facilities, and they say, aha, so you're a manufacturing scheduling software company.
Right.
And say, wait a minute, no, we also use to do to price electricity and electrical power. And then they get a quizzical look on their face and say, wait a minute, you just told me you were a manufacturing scheduling company.
Right.
So yeah, I mean, it is sometimes hard to get across that it's a general purpose tool. It can be used for a lot of different things.
Yeah, the other thing I find too when I talk to folks is that they can fall into two categories. One is when you say, you do optimization and can solve a lot of problems, they're like, great, just optimize my business. And they're not thinking about anything except a magic button and things just happen. Or the converse is they're like, yeah, that's good. And then they start defining all the constraints basically that almost force it to make the same decision that that they would have made anyway.
Yeah, and we also have a bit of a terminology problem because optimization is such a broad term. And so, if you talk to 5 different people and you just say optimization, they come to 5 different conclusions just based on that word. And
yeah, do you ever try to redefine that, like define that more closely? Because we've kind of used the phrase that optimization sometimes means just get better, like just do a little bit better, and we actually mean something different when you're talking.
Right. Yeah. I mean, so this is a problem that the field has had forever, and Informs, the professional society, has tried over the years to come up with different labels. I think one of the most well-known and probably infamous ones was the science of better.
Right.
I don't know if you remember that, but
I remember that. Yeah.
Yeah. I mean, none of them have really caught on. Math programming. I don't know that that's the historical term. I don't know that necessarily is a better intuitive term for what we do. There's mathematical optimization, which basically adds a math component to the word optimization to narrow it down a bit. A lot of times we just say MIP, mixed integer programming, because that's probably the most powerful tool in the optimization toolbox, and it's specific. So it has the advantage that if you say it, it means something specific. It means something precise.
Okay, well, that's interesting.
Also, yeah, it's a pretty nerdy term. So there's that downside.
There's definitely that. Well, let's come back to that one because I want to dive into that a little because we dabble on that one too, and I want to get your take on that. But you hit on something interesting on the sort of the broad range of applications. I think you and I have had this conversation offline. Be good to talk about it here. That kind of what's the range of applications that you've seen, and all the way from sort of the standard to kind of off the wall crazy kinds of things.
Yeah, it's really quite amazing just how broadly applied optimization is. So we'll frequently just do a tally of our customers and the industries they're in, and we typically stop counting at about 40. And it's not just subtle differences between the application areas. I mean, massive differences. So the most common ones among our customers, the most common uses are actually 3 different domains. So supply chain planning. Basically figuring out how to do a better job of scheduling a manufacturing facility, that sort of thing.
Yeah.
Finance, so all things Wall Street, and then electrical power. Electrical power has been growing tremendously over the last decade or so. And the primary application there is unit commitment. So basically figuring out who's going to supply tomorrow's power. Okay. So those are huge, but as I said, 40 plus different domains, and every day we wind up getting exposed to some new application area where it's interesting, it's unusual. One that I've heard about recently that I found particularly interesting is, and actually there are 2 different customers who I sort of would say are doing something along similar lines, which is basically using optimization, using mixed integer programming to fill in missing information. So one example is a guy named Levi who works at East Daily Capital Management, and their business is there are natural gas distribution networks all over the country. So there are mining rigs, there are pipelines that transport the gas, there are processing facilities. And they all have, the system behaves in a pretty well understood way if you actually understand who, where the mines are, or where the processing plants are and who owns them.
Okay.
But the companies that are involved don't actually want this information to be available. They hide it. And so these guys actually have a MIP model where they basically say, well, here's how the system would behave if it were configured like this. If these companies own this, these companies own that. And then they get glimpses of data here and there.
Okay.
There'll be some data that leaks out. They plug it into the MIP model and basically say, okay, here's what we have observed. What internal configuration would actually explain the data that we just saw?
Okay, it's almost like an evolutionary, like taking ideas from evolutionary biology in the sense of like this network must be behaving close to optimal in some way. Let's model it with a MIP and then kind of fill in the points. Is that a good way to think about it, or?
Yeah.
Or not really.
not exactly. So it has some similarities for sure. Yeah. So they get new data all the time. So actually, the other example I wanted to talk about was earthquake fault modeling. So I was talking with a guy at USGS, US Geological Survey, who basically they have an earthquake model that's built as a MIP, where fault lines, if you know the full set of fault lines and how they're connected and all that, then apparently they behave in a fairly understandable way. So if there's an earthquake here, then you can expect stress to build there, and so you can expect an earthquake there.
Yeah.
But the problem is they don't know where all the fault lines are, and they don't know how they're connected. And so it's the same sort of thing. You'll get an earthquake here, you'll get an earthquake there, and then they go and plug these observations into the MIP model and say, okay, what sort of interconnection between the faults would explain what we're seeing?
That's pretty cool. Yeah, definitely. I mean, sort of given that range of like everything from supply chain planning to electricity planning to finance and Wall Street, all the way to earthquake, filling in missing earthquake data. Like, what's your feeling on like how much have we tapped into the potential that's out there for optimization? Are we tapped into 5% of the problems that could be solved with optimization or using it? Or I know it's totally speculative and we're just making up numbers, but what's your feeling? Are we missing a lot? Is the business world and academia missing a lot in terms of where it can be applied?
Oh, yeah, absolutely. Yeah, but I mean, I'm not going to put a percentage on it, but I like to think of it using an analogy. So think about gold mining. So I actually looked it up just before our conversation, and 0.01% of the gold on Earth has been mined.
0.01%?
0.01%, roughly.
Okay.
Yeah, and so that means clearly most of the gold that is on Earth has not been mined. But that doesn't necessarily mean that we should be aiming for 10% or 50% or whatever, because there's some big veins, and a lot of the big veins have been mined, and I'm sure there are lots of other big veins that have not yet been mined. But there's just a lot of gold out there that's just hard to collect. It's just not very concentrated. It's very deep in the ground, what have you. And so you apply the analogy to optimization. There's some optimization problems where there's scope for improvement, but maybe it's just too much work to actually exploit it. Maybe it doesn't. The return on investment just isn't there. The appropriate expertise isn't there. The data is missing, what have you.
Yep.
And then to extend the analogy a bit, I'm skipping ahead, but now we've got the whole analytics field,
right,
where we've got just a brand new focus on extracting value from all this data. And so in this analogy, so I view these these data scientists as people who are mining for something else, natural gas. And so here we have a situation where there's lots of gold in the ground. There's lots of people who are mining for something else, and so it's an opportunity for us, right? Because maybe the right thing to do is to basically just make them aware that, hey, if while you're mining for natural gas you see something that looks like this, well, that means there's probably gold there, and so either let us know, and we will go and figure out how to mine it, or maybe gain some expertise so that you can actually go and while you're mining for something else, you can actually go and exploit other things you find along the way.
Yeah, that's great. The way we see that too, it pops up, is that this, someone's done some great machine learning to come up with some new way to predict something that they haven't been able to predict before. Now they've got this prediction, and they built some nice curves. And then if you can get to that team and say, if you could overlay optimization, you can now take that prediction as an input to an optimization model and actually make a trade-off and sort of balance things instead of just coming up with a prediction.
Absolutely.
Yeah, that's a good analogy. The gold analogy is great, because it's like, yeah, these, I guess data scientists are out there mining for all kinds of new insights, and it's like, can we overlay optimization on top of that to help make a better decision, or even use machine learning to sort of tease out and collect the data and parameters that you didn't have before?
Absolutely.
Feed that in. Yeah, that's interesting. It's got kind of along those same lines of different types of applications. One we've seen is the use of optimization to automate instead of optimize. So, I think when you and I traditionally, if we get together and chat about optimization, we're usually talking about, okay, you solve some problem and you come up with a better solution that maximizes profit or minimizes cost.
Sure.
And, we've seen some cases where, it was very, like a catalog company, for example, it was very complicated to actually lay out the catalog. There's thousands of different rules in there, and just keeping track of those rules was very hard. And the optimization was primarily used just to sort through the rules as more of an automation play than optimization.
Right.
Do better. Have you seen some cases like that as well?
Oh, sure. Yeah. I mean, this is so, as optimization nerds, we see, minimize C transpose X, and we say, aha, we figured out our objective. But yeah, I mean, we definitely, so in a lot of cases, the motivation for doing optimization is just that, there's some person who has some skill, who knows how to, compute schedules, price something, whatever. And that person's, going to retire, or they haven't taken a vacation for 2 years or whatever.
Right.
We just need to come up with some way to automate this process so that we don't actually need to have a lifetime expert involved in the process. And in other cases, actually, we've seen where basically like this is particularly common in workforce scheduling, where the quality of the schedule, sure, that they care about that, but oftentimes the main motivation is just to avoid the perception that some person is making choices that favor one person and harm another person.
Yeah.
So, if you code it, if you code it up in an optimization model, you press the solve button, the computer goes and computes a schedule. If someone wins and someone loses, who are you going to blame? It's the computer that came up with the schedule.
Right. Yeah. It sort of makes it more, at least, I'm sure someone will still blame the computer, but at least it looks a little more unbiased. Related to that, I've seen a kind of a trend with multi-objective optimization and hierarchical optimization, where you, like, let's take that problem, for example, scheduling. Like, one person might have a really bad schedule, but it's optimal from the business's point of view. And then you could think about running other optimizations that says, well, I'm willing to give up, 1% of cost if, the 3 people with the worst schedule get 20% better schedules, whatever that means, how they've quantified that. I think that could be, I feel that's a kind of an interesting way to help automate this too. It's like, it feels like it's how people think about these problems. Like, a manager's never going to save the very last penny if, you could not save that penny and make 50 other things a lot better.
Right. Yeah. And actually, as a tool vendor, one trade-off that we're just constantly faced with is, if there's a capability like multi-objective, we added multi-objective as a feature in the product recently.
Yeah.
And, it took us a long time to add this. And the main reason was basically from an algorithmic point of view, we didn't see a lot of opportunity to do things that are a lot smarter than what you would do if you just went and coded it up yourself. And so, from a value add point of view, we didn't see a lot of value to be added there. But one thing we actually found very soon was that just syncing it in the interface, making it easy to use, just made a lot more people just aware that it was possible, and also just, basically blessed it as something that people, might want to do.
It's legit. Yeah, that's an interesting way. So you just exposed it to give people almost like a marketing thing, like, please use a multi-objective, it'll help you. And then whether they use your feature or not, it doesn't matter, but they're getting more value out of optimization.
Right.
Yeah, nice. So let's go back. Like, how did you get involved in optimization? Like, what intrigued you about this field when you entered it into this area?
Oh boy, yeah. So I did my PhD finished in 1992, and it was in parallel sparse Cholesky factorization, so linear algebra. So so after I graduated, basically, what domains use linear algebra? So a bunch do, but I got interested in optimization. So LP and MIP are just incredibly heavy users of linear algebra. And basically, I just wound up transitioning from being, more of a sort of a pure linear algebra person to someone who was just more applied, who was actually looking at solving some of these optimization problems and using linear algebra more as a tool rather than as the end goal.
Got it. Yeah, that makes sense. I think I was attracted to the field in the sense that it was a way, when you and I were studying it back then, we don't need to get to how long ago that's been. We were, it was like, if you like to use data to solve business problems, like, this was, the kind of the tool to do that. Like, I think now there's many more tools and many more opportunities to use data to solve business problems. But back then it was kind of the one tool or the one area that did that.
Oh yeah.
Yeah, what intrigues you the most about the area? Like, what keeps you going and excited about the field of optimization in general?
I mean, so I've been doing this for 27 years, and I mean, it's never the same from year to year. Every year there's some new application, there's some exciting thing on the horizon, and so it never gets boring.
Okay. Yeah.
It's been a lot of fun, and also as you were talking about, just when I was working in sparse linear algebra, so you have a big linear system, you do something clever, you wind up with a fast solution to that linear system. What business value does that have?
Yeah.
Whereas optimization has the property that you really wind up spanning the whole gamut. You wind up, there's the linear algebra, there's the math behind it. There are the optimization algorithms, the various MIP technologies, and there's the model. There's and at the very highest level, there's the customer application.
Right.
And it's very rare for a domain to allow you to actually see all that. Usually you wind up specializing and you wind up working in one particular part of that whole sort of chain. But in optimization, for reasons frankly I don't fully understand, it's quite common for you to actually be able to see that entire path.
Yeah, that's interesting. I haven't thought about it like that. That's a good take. One You've talked about linear algebra and linear programs and MIPS, and so it might be a little technical. Let's switch to some technical and kind of dive into the detail. Like, yeah, I think it's natural when people talk about linear programs and MIPS to sort of lump those two together. Like,
Right.
do you find yourself trying to explain the difference to people about these two tools and how much harder a MIP can be than a linear program?
Yeah. So turns out that LP is actually a pretty small part of what our customers do.
Mm-hmm.
And most people, by the time we're talking to them, they've got some understanding that, I mean, they know they have a MIP, and they've got some understanding that MIP is just, it's more difficult than LP. The truth is, this is speculation, but I've kind of come to the conclusion that most people, when they come to us and they're solving an LP, so if you look at MIP basically solves a integer programming problem using LP as a subroutine. And it seems that most of the people who are solving LPs using our product are solving some discrete problem and using the LP as a subroutine in their application.
Okay, so do you see many applications of just pure linear programs? Do some industries just use pure linear programs to make decisions, or?
So some do, but I think it's a compromise typically. So I mean, I'm sure there's some, but yeah. It seems everyone that I've been exposed to, nearly everyone, basically, there is a discrete component to it, and the LP is just a tool to make progress towards solving that discrete problem.
Okay, yeah, interesting. That's so what I teach the folks optimization to folks who may not have been introduced to it. And what I see is the number one thing that's sort of gets people kind of confused maybe at the beginning is when they think LP to MIP, what they're thinking of is when they run an LP, they really don't like it that but the answer came back and said, oh, make 23.2 bottles of shampoo. Like, they hate that. They want to make some integer number of shampoo bottles. And I try to teach people, I think the intuition is like, that's not the thing you care about the most. Like, we'll just round that up or down, the number of bottles of shampoo. But what you really want to think about the MIPS is introduce this logic, this if then kind of logic, yes, no kind of thing, and do that. And I think that's the big insight is once you start to get that, then it starts to open up, oh, now I can solve 1,000 business problems with this type of technology.
And if you think about the sort of the canonical problem that motivated the whole field of OR, it's the diet problem, right?
Yeah.
And so the problem that really motivated linear programming, you solve the thing and you immediately say, wait a minute, I'm not going to eat 0.6 of a banana. Once I've peeled it, I'm going to eat the whole thing.
Right.
So even sort of the most basic motivating example for LP, you just immediately look at the solution and you say, well, there's a discrete component to this.
Yeah, so I use a diet problem early in my class, and it drives my students nuts. And it's like, every programming language that you write a linear program, it's very easy to switch from LP to MIP. And I beg them, like, keep it as an LP because you want to use that subroutine, and we haven't covered MIP yet, but almost everyone clicks on the yes integer variable button to see that. I think to your point, it's like your intuition is like, I hate those numbers.
Yeah.
So let's talk about, so now we've got that kind of clear, like, the MIPS are the powerhouse of this of optimization. And one of the things that astonishes everyone from the outside, I think, is just the speed at which these solvers improve. And it's like, I don't know that your exact numbers, maybe you can give some good numbers, but I know it doesn't take long for guys like Gurobi to be 10x faster than you were, just several years ago in solving the same problems. Is there, what metric do you use? 10x is probably not doing it justice. How do you describe how fast it's increased?
So we have a testing methodology, and so according to our testing methodology, basically our current release is like 53 times faster than our version 1.0, and 1.0 was no slouch, so it was state of the art at the time.
Right.
And then if you go back 20 years, 25 years, basically the numbers just get astronomical, and to the point that I think people just stop paying attention to the specific numbers. I think if you go back to using the best methodology that we've got, if you go back to like CPLEX version 1 compared to Gurobi version 8.1, just software alone, it's like a factor of 1 million. And this is across a huge test set. This is not, there's one model that's 1 million times faster. These are, average numbers across a broad test set.
Right.
And so, a factor of 1,000,000, it's hard to even, difference between 1,000,000, 10,000,000, 100,000,000, these are all big numbers. What's the difference?
Right.
And so, the key point is that the capability of the software it's just order of magnitude different.
Yeah, and I should point out, I'm pretty sure, you guys are very careful when you do these tests, and you make sure you're taking the machine capability out of the test. And
Right.
this is just the speed up you get from the algorithms and the software, not the speed up that, we've seen a similar speed up probably in the hardware side.
Quite a
Or
bit
maybe
less.
not.
Quite a bit less, yeah.
Quite a
So,
bit less.
you combine a factor of 1,000,000 in the software, maybe a factor of 1,000 in the hardware, and you get to 1,000,000,000. The numbers just get ridiculous at a certain point. And I mean, again, the key point is that, not that you have to take your expectations and, from 20 years ago, divide everything by 1,000,000,000, but really it's that you have to take them and throw them away because they're out of date.
Yeah. So how have you guys done that? How have you maintained the increase in speed? Like this is interesting technically, and I think it'd be interesting as just like a Harvard Business Review case study from a business point of view. Like how has this happened? Like what do you think are the big drivers of this continuous improvement?
Yeah.
Without giving away any secrets.
Yeah, sure. So I think the key point is just that that the demand for performance is for MIP performance is just insatiable. So people just keep, you create a solver that can solve their current problem in a small amount of time, and they just create a bigger problem. And so, the problems have just continued to grow. And MIP it's difficult. And so, when your problems grow, basically your runtimes grow, and it just exposes new opportunities to improve things. And so, in terms of, where do the ideas come from? It's not one thing. It's not a small set of things. It's a very, very long list of things. So a typical release for us will have, 20, 30 ideas that each contribute 1% or 2%.
Okay.
And, where do the ideas come from? So, we hire smart people. We've got an incredibly talented team. And, over time, basically, if you've got something that's improved by a factor of 1,000,000, then the things that were the bottlenecks, the things that were, important for performance 10 years ago, but probably not so important anymore, and there are new things that are important. And so there's a sizable part of the process which is basically just being exposed to new bottlenecks and tackling them.
All right. That's interesting. That reminds me of the Toyota production system in some sense. It's like there's no one trick. It's like working on lots and lots and lots of little things that over time starts to add up to some big improvements in how things work.
Absolutely.
Yeah, and I'm sure you're still running into the P doesn't equal NP problem, and so you still run into long run times, and then that just encourages you guys to go back and think harder about sort of where the bottlenecks are. And
absolutely.
Yeah. You said something that struck a nerve with me. I was doing a lot of supply chain planning early in my career, and it's over like a 8-year period. I thought, well, in 8 years from now, like these models which take 15 minutes will now be running in like 2 seconds. And what happened in 8 years later is they were still running 15 minutes because people just every time you could get faster, they added more stuff to it. So it's I think you're seeing kind of the same thing.
Oh, absolutely.
So you talked a lot about MIPS and linear programs, and so one thing I want to touch on is nonlinear programming, to see what your thoughts are there. Like my understanding, and maybe it's outdated, is I think I had a professor at one point or someone who told me basically they were talking about nonlinear programming. Their advice was don't do it. Like from a business modeling point of view. But where has it come? Am I thinking out of date? And have you seen improvements in nonlinear programming?
So MIP is in this interesting sweet spot. So it's an abstraction. It's a problem that you can state where, for the most part, we can solve it. You can certainly formulate problems that can't be solved, and you may have to adjust your formulation or rethink some things. But for the most part, if you're confronted with a problem that can be solved by MIP, you can probably come up with a formulation where you can solve it. And so what that enables us to do is, sell a product to a customer. The customer builds a model, embeds it in an application, and then forgets about it.
Right.
And nonlinear programming just doesn't have that characteristic. I mean, it just isn't in the sweet spot. You can't, well, in general, you can't just formulate a model, sync it in an application, and then just ship it and not have to worry about it, solving all the problems that you're going to be confronted with.
Right.
And so what we've been doing over the years and are continuing to do is just try to figure out how to expand the sweet spot a bit. So I don't think we'll ever produce a general purpose nonlinear solver that's geared towards solving every NLP. But over time, so at one point we added MIQP, quadratic objective, and then we added MIQCP, quadratic constraints. In the next release, we're actually doing bilinear.
Okay.
Z equals X times Y. And there are applications that need bilinear. It's also a nice building block for doing other things. And we're convinced, we're comfortable that bilinear is a problem where if you state it, we can, the likelihood is very high that we can solve it. But I mean, we'll certainly continue to try and push the envelope to try and sort of pull in more nonlinear things that still live in this interesting sweet spot.
Yeah.
But it's a slow process, and the notion that there will be a nonlinear solver that can it's a black box that you just hand any problem and it just solves, that we're far away from that.
All right, at least my data is not out of date, because it's I get the feeling you kind of push because naturally people think of the linear constraint in either a MIP or a linear program as like way too restrictive for the real world. And what I try to tell people is that MIPS can give you a lot of flexibility to sort of approximate the nonlinear parts of your problem. And I think to your point, like they give you an answer, and you can add side constraints. Like, maybe if you have a nonlinear problem, maybe you can solve it once or get it solving, but as soon as you add a side constraint, it might break the whole thing. Has that been your experience as well?
Yeah. And I mean, so people often ask, can you solve nonlinear programming problems? And the answer is people use our product, use MIP to solve nonlinear programming problems every day.
Right.
They've done approximations. So it's very common for a MIP model to have some sort of piecewise linear function, which is in fact a nonlinear function that just has been approximated.
Yep. Right. Yeah. I kind of my statement to people is that you can solve a MIP, approximate it, and get a solution with a MIP, or you can model it directly as a nonlinear problem and not get a solution. And I think getting the solution is a better alternative.
Yeah, sure.
Now I think about that. Let's switch a little to maybe some technology while we're kind of on the tech side here. Just talk about a little bit about your philosophy. And I was going to hit some open source in a minute, but let's start with the fact that you guys didn't write your own modeling language per se. Like you just built a package in Python, which might have been an interesting decision when you guys came up with Gurobi 1.0 or whenever you came out with that package, because I don't think Python was as popular then as it is now. So how did you think through that?
Yeah, interesting decision is a generous way to put it. I think a lot of people thought we were nuts. Yeah, and the thinking at the time was that if you create a new language, then there are pluses and minuses. The main pluses is, of course, you can tailor it to the domain.
Right.
But the main minus is basically you're stepping out of any ecosystem. You're trying to create your own ecosystem. And one thing that was apparent at the time about Python was that the ecosystem was growing quickly. 10 years ago when we first did this, it was much, much smaller than it is today, but it was still sizable. And so, we as a new company, a small company, we could either go and, have the, boldness, arrogance, stupidity, whatever you want to call it, to basically, we're going to create our own ecosystem. So we're going to build a new language, and then people are going to flock to it, and then they're going to add libraries, and so you'll be able to do, databases and GUIs and machine learning and who knows what.
Right.
Or we could just say, look, this is emerging. We think that we can get to a point where, you can get most of the expressiveness of a modeling language within a general purpose language, and you get all the benefits of being inside an incredibly versatile and well-supported environment. So that was the calculus back then. It seems to have paid off.
Yeah, it seems to have paid off great. I mean, it seems like other solvers sort of follow that, and it seems like that this is the modeling language of data scientists is Python.
Yeah, yeah. And that, I'd rather be lucky than good. So
Yeah.
yeah, sure. I mean, some of that was vision or
How long
foresight
did
or
you guys
whatever.
debate that? Like, how long
But
did you debate it for? A long time? And I mean, it must have been an interesting debate because some of you on who were debating it must not have known Python or like just knew of it, but weren't totally into the language.
yeah, I wouldn't say it was a debate so much. At the time, basically, the alternatives were not, at the time, were not, either do a Python language or create our own language. At the time, the alternative was, there were the three founders.
Yeah. Okay.
We were writing code as quickly as we could.
Yeah.
And it was a choice between, having a Python interface or, putting something on a roadmap for several years in the future. So necessity played a big role as well.
That's great. Someone at some point told me that, from an optimization point of view, sometimes constraints are actually pretty good. So you had a constraint that you couldn't do your own language. And so this turned out well. So yeah, it's the tide has definitely turned. So I've been teaching optimization in an analytics class. So these are students who came in for like a machine learning type of degree, and they take an optimization class. And I've only been teaching it for like 5 or 6 years since the program started. And I used standard modeling languages or pre-built when very nice algebraic notation. And the students kind of hated it because they all knew Python. And as soon as I showed them Python, immediately it was clear to me that I had to switch over and teach the class in Python, or the students were going to revolt. Like they didn't want to learn some custom language, even though the algebraic notation was like sort of really expressive and perfect for this particular problem. They're like, nope, I already know Python. So, your choice was good. So speaking of open source kind of things, so what do you think about open source solvers? So there's a small group of open source solvers out there. Like, how do you think about those?
Yeah, it's great that they exist, and they do provide a way for people to get introduced to the technology. It's a tough situation though, because in terms of their ability to solve difficult problems, they're not so strong. And so, on the one hand, they make it easy for new people to get exposed to optimization, but on the other hand, they potentially leave the wrong impression about what the technology is capable of doing.
Mm-hmm.
And so, we're always kind of walking a bit of a tightrope because, on the one hand, as I said, it's great that they exist.
Yeah.
But on the other hand, I mean, it really is important to get the message out that these things do not really reflect the state of the art. And if, the risk here, of course, is that, someone who's new to optimization, they grab open source, they formulate their problem, it doesn't solve, and their conclusion is, I guess MIP just isn't a very powerful technology. It's not able to solve my problems.
Right.
And it's in other fields, open source in terms of the level of the technology, and in a lot of fields it's at the state of the art, or sometimes a bit behind, or is the state of the art.
Right.
And so a lot of people just have the expectation that, oh yeah, the commercial tool, sure, maybe it's better supported, maybe it's a bit more polished, but the open source is going to be just as good. But in our domain, it's just not the case.
Yeah, no, I've seen that. I mean, you can't say this, but I can say it. When we do tests side by side, it's like the open source is 6 to 10 times slower, and that stuff matters. When you formulate a problem that takes 30 seconds or a minute, multiply that by 10x. Now you've gone from something that looks fast to the user to something that looks very slow to the user, and we've encountered some bugs in some of the open source solvers as well, and it's hard to sort of figure out what's driving that. So. I agree. It's sort of it lets people dip their toe in, but we need to work hard to educate people that for the smallest applications, for tiny applications, maybe they're okay, but use caution. And there's the commercial stuff is state of the art. I think you said a great. I was going to ask why is it so hard for the open source to sort of keep up? And I think you hit it with the 20 or 30 different bottlenecks that you have to fix in each release. There's just a lot of work to do to engineer these solvers to work well on a wide range of MIPS.
Right, and there's also, if you look at successful open source projects, I think there's a bit of a pattern, which is that they're built out of necessity. So someone once has a need, they want to do something, and the tool doesn't exist, and so they go and build it.
Yeah.
Or there's an existing open source project that doesn't have a feature that they want, so they go and add it. And optimization, or MIP, has the property that the distance between the typical user and the technology that underlies the product is just massive. And so, someone who is using who's building a MIP model, trying to solve an optimization problem, they're not experts in linear algebra or cutting planes or parallel computing or any of that stuff.
Right.
So there, in this domain, there seems to be a pretty big gap between the sort of the interests of the people who are using the product and the backgrounds that are required in order to advance a piece of software.
Yeah, so let's talk a little bit about some research I know you did on optimization and data science. So I know you were curious about this, so you attended a talk of mine a while ago, and you've been doing some research trying to figure out, like, what is this data scientist movement all about, and where does optimization fit? And what'd you find when you sort of dug into that, and sort of what surprised you?
Yeah, I mean, it's a process we're continuing to do.
Yeah.
Yeah, I mean, data science is a huge movement. It's important for what we do. I'm sure it's important for what you do, probably more important for what you do than for what we do right now. Yeah, I mean, so the main, in terms of high-level conclusions, number one, having a larger group of people who are interested in taking a quantitative approach to business data, that's a good thing.
Right.
And, forget the technology for a second, whether it's machine learning or MIP or whatever, just having a demand for people who are actually, quantitative people inside of companies, this is a good thing.
Right. Couldn't agree more.
And, and also, data science. So, the first word is data. And so, having people who have a focus on data also means that, companies have, that focus extends to, making sure you have the right data, making sure that you have high quality data. And, whether you're going to use that for machine learning or optimization, whatever, we all want more data. We all want high quality data.
Right.
So this is all good. Yeah, and as far as the technologies go and how they relate to each other, I mean, one of the main things we found is just that the integration between optimization and machine learning, it's still pretty loose.
Mm-hmm.
So the typical application that uses both, basically, you use one, you set it down, you take the output, and then you pass it to the other.
Right.
And so you use a machine learning model to come up with predictions, and then you take those predictions and you feed them into an optimization model to figure out how to act on the likely outcomes. Or another scenario we've seen recently is you have a bunch of scenarios, and you use an optimization model to figure out what the best course of action is for that scenario. And then you go and use a machine learning. You capture that as a bunch of data, and then you use a machine learning model to say, well, I know what the optimal choices are for these scenarios, so now maybe I can come up with a model for how to make a good choice given the range of possible inputs.
Right.
And there's lots of academic research on tighter integration. I haven't seen. I mean, at this point, I don't think I've seen any of it sort of make its way into practice. It's clear that it's coming. Optimization and machine learning, the problems that underlie machine learning are fundamentally optimization problems.
We're seeing something similar too, where there's I think a big trend to figure out how do I get enough data on a system, and maybe I have to simulate that system. And to simulate it, I'm using that term broadly too. I might have to run a whole bunch of MIPS to kind of simulate what I would do,
right.
And then use some other technique like reinforcement learning or deep learning to sort of extrapolate from the simulation to, like what you said, to
exactly.
sort of now totally new situation. I didn't run any kind of plan for it, but what should I actually do in this new situation?
Yeah, and people, it's interesting. It's interesting because a lot of people find that to be unsatisfying. They don't view it as sort of the tools, the techniques being combined. They view it as basically just a handoff.
Yeah.
I don't share that view. I understand the viewpoint, but I don't really share the view because there are lots of different domains where you take different tools from different places, combine them, and you wind up with something that's much more powerful than either one alone.
That's right. Yeah, that'll be interesting to see how that evolves over time. I think that's a trend to keep an eye on.
Absolutely.
Yeah, let's kind of wrap up with kind of future technology and sort of where things are going. So let's start with quantum computing. So I know, when we talked about this, you're like, do you want to know my answer? And I said no. So I'm curious to see what you think about quantum computing for optimization, because this is the use case I see a lot. Is people say, quantum computing is going to really help in optimization. So
Right.
could you explain, like, first, like, what you understand it, like, what is the promise, whether you believe in the promise or not, and then comment on sort of where you think it's going to go.
Yeah, and so I mean, ultimately, the promise is that there's certain types of problems it can solve much faster. And in particular, there's one optimization problem which is really, it's right in the center of quantum computing, which is QUBO, quadratic unconstrained binary optimization.
Okay.
So that is a problem. A quantum annealer, which is a machine that exists, you can actually buy a quantum annealer now. A quantum annealer solves exactly that problem. And so we've actually had some companies in the space come to us and say, we're working on quantum computing. Quantum computer can solve QUBO. So what fraction of your customers' models are quadratic unconstrained binary optimization? And I think we can both answer that question. It's zero. It's not a practical problem. It's an interesting problem that it's interesting that it can solve it, but it's not a practical problem. And so then, there's just a lot of excitement, of course, around the notion that there are going to be a class of computers that can solve problems that are just unsolvable today. And, the fact that there exists an optimization problem that's sort of in the mix, puts optimization in play.
Yep.
But, at the same time, so, QUBO is not a problem that people want to solve, but it directly. But it could be an interesting subroutine. Could be some clever ways to use this to build something that can solve a bigger problem. And so it's exciting to be able to have a technology that can solve a problem that is related to the problem you want to solve quickly.
Yeah.
But the thing you have to keep in mind is that we already have that. That's linear programming, right?
Right.
And so the notion that this fundamentally changes the sorts of problems you can solve in optimization, we're not there yet.
Okay. And it sounds like you're skeptical that we might not be there for a long time. It might be quite a bit there.
Yeah, it's gonna take some clearness for sure.
Yeah. So what about other technologies like distributed? Oh, go ahead. Sorry.
Yeah, one more point. So one thing I find quite interesting is that when you read articles about quantum computing, particularly in the trade press, there's lots. They quote people who are really excited about the possibility that someday we'll be able to solve this optimization problem and that optimization problem. We'll be able to do this more efficiently, that more efficiently. And in a lot of cases, these are problems we can solve right now.
Right.
And so it's captured the imagination of people about what's possible in the future. And in a lot of cases, this isn't the future. This is today.
Yeah, I think I've seen some more points. I don't know if they've had an exact example, but I could imagine someone in quantum computing saying we can solve the TSP quickly, and then someone in OR would be like, yes, check.
Yeah,
we're doing it. What about stuff like distributed computing? So cheap GPUs, things like Spark, where you're using multiple processors to parallelize the optimization. Like, my experience with it in the past is, again, this might be dated, is it wasn't that effective when I saw it. It was a little bit better, but not much better. What's your thought on that now?
Yeah, so we have a product that solves MIPS on a distributed machine.
Okay.
And there's some models where we can get a 50x speed up on if we grab 200 machines. They're rare.
Yeah.
The thing that is often counterintuitive to people is, so to solve a MIP, it's a branch and bound tree. So you're exploring a tree.
Yeah.
And tree search, just intuitively, it's trivially parallel, right?
Yeah, it seems that way, right? You would think just go down lots of different branches and lots of different processors and.
Right, exactly. But the thing that sort of works against us in the case of MIP is, earlier we're talking about the improvements in the technology. So for the most part, when we make the MIP solver faster, we do it by exploring fewer nodes.
Okay.
So doing smarter things, at the root node. Generally, do smarter branching, smarter this, smarter that. Generally, the the way to achieve higher performance is solving fewer nodes. And so, by that measure, basically every release we're working hard to reduce the amount of parallelism and the opportunity to exploit lots of cores.
Right.
So, at this point, out of the box, our product is parallel. It uses all the cores on a machine. And on a 4-core machine, I think our average performance improvement across a broad set is just over 2x.
Okay.
We get, if you got an 8-core machine or 16-core machine, it goes beyond that. I think 16-core, the average is close to 4x, something like that. But the notion that we can use hundreds or thousands of cores to solve these models, for whatever reason, we're just not there. We just haven't figured out how to do it.
It's interesting. So it sounds like there's big diminishing returns. Like going from 1 core to 2 probably gets you a lot of 70% of your benefit, and then 2 to 4, and then it starts to slow down at some point, right?
Right.
Yeah, interesting. All right. So what's anything big on the horizon that we didn't hit that we should talk about? Any interesting technologies you guys are following that are worth mentioning here?
In terms of technology trends.
Yeah, like technology trends that you guys, you're watching that will help speed up MIPS in the future or help.
Right. Yeah.
Or any closing comments you might have on sort of just the overall value of how people should be thinking about optimization.
Yeah. The technology. So we talked about the improvement over time, and technology keeps improving. And so our role is just to make the tool as powerful, and also just to expand the set of problems you can solve. And the fact that there are all these data scientists out there who are looking for new opportunities to pull value out of this data. I think fundamentally that's the thing that's going to be driving the field into new directions. It's not a small effect. I mean, the number of data scientists who've been hired by companies over the last couple of years is just, compared to the number of optimization people out there, it's a massive increase in the analytical capabilities.
It's huge. Yeah, that's a trend we're seeing. It's just it's fundamentally different.
It's absolutely massive. And so the technology will keep moving forward for sure. But I think a lot of the exciting stuff is just coming from the fact that there's so many people out there who are just looking for new ways to pull value out of all this data.
Yeah, perfect. All right, well, Ed, thanks for your time. Let's maybe open it up for questions, but I totally appreciate you taking the time to chat. And if anyone has any questions, put them up on the board there, and we'll answer them.
Great. Yes, thanks to both of you guys. This is a great session so far, and we definitely have a few questions lined up for you guys. So let me get to the first one. So the first one is around, just in general, when setting up optimization problems for business, what are the common constraints that you've run up against that directly impact success, or as I would assume, not success?
So actually, I think that's probably more of a question for Mike. So as a tool vendor, so we're providing tools to the folks who are actually building the models, and we get pulled in. We get some exposure to how it's actually being used. But I think Mike, probably you're going to be closer to being able to give a good answer to that question.
Yeah, we've talked a lot about MIPS here. We definitely encourage people to think about, can we minimize the number of integer variables that we really need to have to get started? So, I think the initial reaction is like to throw almost too much into the model. And the second problem that people run into is they don't think about what to do when there's an infeasible model. So, some constraints like, especially like minimization constraints tend to come back with just infeasibility messages rather than sort of point to where you're tight. And so we think it's important also to sort of have safety valves when you set up your model, just so that it sort of always runs. So sometimes these are called slack variables, or you can do it some other different ways, but the idea is like, how do you make it broad enough so when I hit the run button, I come up with some answer. That answer might not be feasible, it might not be practical, but at least tells me and points me in the direction of sort of what's wrong with my model. So we kind of give that advice, and we see that as we get these things set up.
Gotcha. Interesting. Okay, so the next one is probably more of a broader question, and maybe again could be answered by both of you. But this person is pointing out that during the chat here, you guys talked about how ML and optimization are somewhat mutually exclusive. But do you feel like there's a perception in the industry, and this is a loaded question, that ML and data science are more impactful than optimization? And the direct quote from this person is, "I never see as much excitement about optimization as there is for ML."
Yeah, it's definitely true. Yeah, and Mike and I have chatted with this before. I think it's a lot of probably most optimization people have had a conversation along these lines. To my mind, this is basically just the fact that optimization has been around for longer. And my daughter, when she was 2 years old, if I plotted her height trajectory, it would be easy to conclude she was going to be 12 feet tall when she grew up. And the fact that optimization's been around for a long time, we know how, at this point we know what it can do. And there are always new things, of course, being discovered, but sort of the edges are known, are understood. Whereas, with machine learning, it's a new technology. It's being applied in new ways, and so don't necessarily know where the boundaries are.
Yeah, I think what we're trying to do is trying to define this whole field of basically AI. How people are using the term is a big umbrella term where optimization fits in there, and machine learning fits in there, and deep learning fits in there, and all these algorithms fit in there. It's just a collection of algorithms that people can use to sort of automate and make better decisions with the data that they have. And we've kind of found some success in that, and we're starting to see some trends where people who are heavy in the machine learning and data science have sort of discovered linear programming and what it can do to help them solve particular problems. So hopefully optimization can jump on this marketing bandwagon at least and realize that, hey, this is an algorithm that should be in your toolkit. And it might not apply to all problems, but it should for sure be in any data scientist toolkit.
And so the claim I often make, and I get a lot of pushback, but I think it's true, is that just in terms of the impact on business to this point, the impact of optimization absolutely dwarfs the impact from machine learning. And again, optimization's been around for longer, and so that certainly plays a role. And I think the impact from machine learning will continue to grow for sure. But if you talk to most people who are writing trade press articles about machine learning, and you tell them that optimization is a technology that's been out there for a while that is not so visible, that has had a much bigger net impact on on businesses, I don't think they would believe that.
Yeah, I mean, you almost want to point them to the airline industry or something, Ed, just to say, like, the whole airline industry is built on the back of optimization. Like, the prices wouldn't have come down like they have, and the efficiencies wouldn't have gone up without optimization technology.
Oh, you can point to half a dozen industries that are just they're just absolutely transformed by optimization.
Sure. Interesting. Okay. So one more question that came out when you guys were discussing nonlinear optimization problems, it was, how about stochastic optimization and the current state of practicality for applying that?
Yeah, this is so George Danzig back in the 1950s. So when he was, he developed the simplex method. From what I understand, so the problem he was really trying to solve was stochastic optimization, and he worked on it for probably 30 years, something like that. And one thing I can tell you from the sort of the application side is it's very, very rare for us to see an application that includes a stochastic component. And the explanation in almost all cases is, if you've got some time to spare, ultimately you've got a budget for how much time you can spend on your optimization. So you have a choice. You can either add more data or more detail to a deterministic model, or you can add a stochastic component to it. And I mean, so far, almost everyone is choosing to add more detail.
Mm-hmm.
Yeah, you think it's because of I think some of it's maybe the probabilities are hard to estimate, and then the other, even if you get the probabilities in for simple models, it's actually hard to interpret the results. Like, what does it actually tell me? And do I believe it?
Yeah, that's true. That's true as well.
Interesting. Okay, well, we are rapidly approaching the top of the hour here, Ed, but I have one more question. I think everyone on this call would be very interested in hearing you sort of give an answer on is, what is your advice to the students on this call looking to become optimization experts?
Oh boy. Yeah, and so I guess so. My main advice is that the applications are the interesting stuff. So it's useful to have a background in simplex method, a small background, simplex method, branch and bound, cutting planes, those sorts of things. But you very quickly get to a point where you have what you need to be a user of the technology. And I mean, to be an expert is really mostly about being exposed to lots of different models that have been built, and being able to walk into a situation, see here's the data that's available, here's the here are the things that are driving profit, cost, whatever it is you're trying to optimize, and here's how I can build a model that will capture that, and and without requiring a year or two to go and implement and deploy. So my advice is expose yourself to lots of different optimization applications, because the number of truly different, fundamentally different models that are out there is not that small. Sorry, it's not that big. So there are maybe 10, 20 different sort of types of models, but there's a lot of cleverness in figuring out that for this problem that this customer is trying to solve, I'm going to take this model, modify it in this way, and I'm going to wind up with something that's going to be able to solve this problem.
Cool, interesting. All right, thank you very much, Ed. I think we can't say thanks enough for you jumping on the phone with us today. I think it was a really interesting conversation. Mike, thanks for sort of running the interview, and thanks everyone else for joining us today.